Use this one. Okay. Okay. Thanks for staying. Tempo is in terrific shape. We're on time. We're on budget. Much more detail later, but we have gone into the implementation phase. And before I go too much further, my co-authors and I would like to just dwell on the logos at the bottom for a minute. Of course, it's proposed out of the Smithsonian, but it is the first NASA Earth Venture instrument. But in addition to that, the instrument project is managed for us by NASA Langley, and the mission project, which provides the ride and the platform, has been directed to NASA Langley. The instrument is being built by Ball Brothers. I've worked with Ball Brothers on Skiamaki, on OMPS, on Geotazo, so they're an obvious choice, and in retrospect, obviously the right choice to do that. So without that kind of support, there would be no Tempo. It's been a wonderful experience working with these folks. So I'm not going to go in all of the detail. These are geotazo spectra over Denver and the environment, so that's what it might look a bit like in the future. But I do want to point out the basic Tempo science questions that we're addressing, and basically it is, what are the emissions of gases and aerosols having to do with air quality and climate? Good, now I can see one of them. And how do those inform the processes that determine tropospheric composition and air quality over the various temporal and spatial scales? What is the relationship between air pollution and climate? And how does climate change affect air quality on the continental scale? How can we improve, together with our investigators from NOAA and the Environmental Protection Agency, air quality forecasts and assessments? How can we continue, as we have from low Earth orbit already, to look at intercontinental transport of pollution? And finally, we have the ability, when and if there are episodic events such as wildfires, dust outbreaks, and since we go down to Mexico, even volcanic events, to look at even greater temporal resolution than our normal hourly resolution. Okay, so here's what the project looks like in a nutshell. So it's us out of the Smithsonian Astrophysical Observatory. Shang Liu here is the deputy PI. Jay in the corner there is the deputy instrument scientist, and Alex is our headquarters person. And there are a lot of science team members out there in the audience. So it's managed by Langley, as we said, but we have a lot of other government agencies, NASA centers, and universities on board. We have a robust international collaboration with Korea, the GEMS instrument, with the United Kingdom, particularly in ozone stuff. You saw Georgina represent that in the beginning of this session. Canada and Mexico, since we are the Canadian and the Mexican air pollution instrument. So we're selected, we'll deliver in May 2017 for a launch no earlier than the end of 2018. It's a UV visible instrument of the sort of which there are a number in low Earth orbit at the moment. So we have a lot of heritage in doing the kinds of fittings that we need to do, and we have the ability, as we're starting to see, to distinguish boundary layer from free tropospheric and stratospheric ozone. This is the structure of the project, which I don't think I need to dwell on. This is the view from geostationary. Joe is our administrator at SAO, and he is at geostationary. The low Earth orbit satellites we've been hearing about are at about an eighth of an Earth diameter, so they're going around in here. That sort of gives you a sense of the difficulty in doing the pointing necessary to do the measurements that we need to do. You saw this figure before in Jim's presentation. I'm using it here as an example to emphasize how important it is to have hourly measurements as things develop here in the surface and NO2 columns, compared with the once a day or maybe twice a day measurements you get from low Earth orbit. So a bit more about the instrument. The measurement technique, it's a UV visible spectrometer of modest resolution with CCD detectors. You'll see the field of regard in a lot of detail in the moment and how the pixels lay out on it. So the spatial resolution at the center of our field of regard is just under 10 square kilometers, and it varies then with the Earth's geometry from the viewing condition. And some products will be produced on that native scale, some will be co-added a bit in order to meet our measurement requirements, most of which are hourly except for a few of the gases, but we have formaldehyde, glyoxal, SO2, ozone, including the boundary layer ozone. There will, and other scientific products that will be on a later slide. Okay, we mentioned the resolution, and we will measure up to 50 degrees for SO2 and higher zenith angle for the other products. Here is the spectrometer being developed for us by Ball Brothers. I'm not going to dwell on it, but it's an Offner type spectrometer that is similar to the Jim's instrument they're also building. You saw a bit of this before in Georgina's talk. This is the range of our two CCDs in the UV and the visible, and they're overlaid over some GOM1 spectra that I picked to sort of show the range of conditions that you see on the Earth when you're measuring these spectra, or if you're an astronomer, what you might expect to see on an extrasolar planet. We are in the thick of developing the algorithms. They're going very well because we've done all of the measurements that we need to do to the accuracy that we need to do them from the low Earth orbit satellites, but we have to arrange to make them work for the speed and from geostationary with different pointing conditions. We're exercising them here on these next couple of slides with OPS, which is quite a lovely spectrometer. So this is some OPS formaldehyde and OPS NO2, which is turning out to be quite nice, even though it's not optimized to be in the region where you would normally fit the NO2. The mission then is a geostationary commercial telecommunications satellite. The launch will be, the orbit will be at a longitude as close to 100 degrees west as we can get it. Here's the acceptable range. And we will have selected a platform and therefore also know the launch date next summer. And then we'll do hourly measurements at least up to 70 and hopefully longer than that if we can. I mentioned the heritage, I think, several times. So here are the molecules again. Our colleagues at NASA Goddard are providing us with cloud and aerosol algorithms. And we will also implement a UV index collaborating with our colleagues from Finland. And then there'll be higher level products, so near real-time pollution and air quality indices. Oh, I mentioned the UV index before. And then research products of the sort that we see with the other satellites. You saw a lot of BRO at this meeting, and BRO is not normally an air quality gas, but since we see it from all of the others, we know that it will be very robustly measured with tempo. And we hope to develop additional aerosol products, perhaps by our co-chair here, and vegetation products, again, from colleagues at NASA Goddard. So here's the broad look of the field of regard. Right here at the center, it's the size, 2.1 north-south, 4.7 east-west, and it's 2,000 steps north-south, 1250 east-west, working in this sort of fashion. So this is an hour's observations, except this is OMI data, so tempo will be a lot higher spatial resolution than this. So you can see how we're sweeping over Mexico City. Hopefully by the time we launch, the US and Cuba will have normalized things to the point where we can also become the Cuban pollution monitoring satellite. No, because look, we are doing them each hour. This is a slide that, it shows up fine here, but not so fine there. It's cut off a little, but it shows what the footprint is like at various locations, like down at Mexico City, about 7.5 kilometers, about the same at Havana, and up at the oil sands of Canada. It's at its worst because it's so far north and the Earth is curved, but we're still about 20 square kilometers, so it's quite nice. Here are products, again, with uncertainties that I don't really need to go into. I do want to point out that we want to have near real-time products so that you can have apps, say, on your mobile device to decide whether you can go for a run that day or whether it's safe to play outside or whatnot. So we're here, right, just about, I guess, right in there. And that here is nominally what the coverage will be over the Bay Area, right, every hour. And if you're down here in Mexico City, the coverage then, Mexico City is larger, of course, and that would be what we would see there. And similar in Cuba, of course. We've seen the constellation several times, so here it is again. It would be nice if the constellation grew, but our job at the moment is to make this one work. We're very closely coupled with our Korean with the European colleagues and the Korean colleagues, but particularly on algorithm development and instrument similarity with the Koreans. Our colleagues at the EPA are working with us to provide this remote sensing information gateway, which we're going to employ so that those of you who don't want all of the data products and don't want to drink from the fire hose, but might want to do subsetting in time and in space and regridding and choosing the format that you want them in, you'll be able to go to the server, use this tool, and download the parts that we want. There's a lot of effort in the community to try and make data more user-friendly so that a person who's not a professional at drinking from the fire hose can have access to useful science. So I think I'm turning yellow here, and finally, I mentioned we are on schedule and on budget. We've passed several reviews. We've worked hard with Ball and with Langley to resolve technical issues, and there are no particularly tall poles at the moment, and Jay is nodding his head in agreement with me. We are in a conditional phase C until we have our KDPC in March, and so we've ordered most of the big stuff. The costs haven't gone up on it significantly. The ground systems are at our place on schedule. As I mentioned, we'll have a host next summer, and we will be ready to launch as soon as we are integrated onto the host, which should take about a year. And with that, thanks for your attention.
So we have time for a shoot of questions.
Yeah, concerning the field of view, is it the final field of view, like, because it seems to be very wide, like over oceans and over Canada and over Mexico. So my question is, if you narrow down the field of view, can you increase the temporal and spatial resolution?
We would have to redesign the instrument in order to do that. So we have no knob to turn from the ground for that.
Yeah, we can improve the temporal.
We can improve the temporal resolution simply by scanning part of it more often.
Yeah, for European geostationary satellite, what's giving us a lot of concern is how to correct for the background signals. What's the strategy for tempo? Correct for stratospheric NO2 or background formaldehyde?
Well, for stratospheric NO2, the approach is going to be determined by team member Randall Martin, who's worked with a lot of the people in here, and whether it will be strictly a sector method or something else, I don't particularly know right now. For background formaldehyde, I don't know whether we'll have the same issue that we've had with OMI, because it might be more of an instrument issue there, and it's a different instrument.
I was more referring to the background from methane oxidation.
Well, we wouldn't want to correct for the real formaldehyde. If we have background formaldehyde from methane oxidation, it would be part of the formaldehyde that we measure, and we wouldn't want to correct for it. Unless I'm missing something in your question.